Hello guys, so before we proceed with some problems on lateral and supported beams, we need to first understand how do we determine the modification factor uh, for the moment gradient, CV. So this moment gradient, CV is a modification coefficient for a non-uniform bending moment variation for a beam segment laterally unbraced at segment ends. Okay, so we are referring here segments. Okay, let me first set my graphics pen for a minute. Okay, so I'd like to make emphasis on the word segment here. If we have a beam, any type of beam, supported somewhere. So for the application for the moment gradient is actually done based on the segment ends defined by the bracing. So if I use a symbol X or a cross here, okay, to refer uh, to a lateral brace, so this is to differentiate it from a support, okay? So this is a lateral brace, say here and here. The computation for your moment gradient CB is actually based uh, for a single segment. Say if I define these brace points as 1, 2, and 3, I may determine or may consider this as my segment 1, 2. Okay, and this is segment 2, 3. Of course, for purpose of uh, considering symmetry, we can say that segment 1, 2 and segment 2, 3 may be the same, depending upon the position or the location of your uh, brace point. You call this now brace point 2. Okay, so this is a lateral brace point. Okay, so in the determination of the CB factor, then we have actually two formula. So this formula I did not include in my lecture because this is already an old formula, but still very useful even today. Okay, so this is based only on end moments. Okay, M1 and M2, where M1 is always the smaller value. And the other formula is the new Formula 1993 by Kirby and Nethercutt, in which the RM term is not yet included and was only included during the AISC 2005. So RM is to account for the monosymmetric sectional condition, which is normally taken as 1 for doubly symmetric shapes and single symmetric shape with the same curvature. Okay, so we may consider for starting point Rm to be equal to 1.0. And of course, the minimum value of CB is always greater or equal to 1.0. So for the new formula, the moment are no longer considered at the ends, but rather the end of the segment, sorry, but they are considered at quarter points. Okay, so we have here, if this is now my brace point 1, brace point 2, and brace point 3, I have to subdivide this to quarter points. Say this is 1, 2, and 3. So this is my A, B, C. So considering, of course, only for this segment. So I have here my segment 1, 2. So if I draw the moment diagram of this, say here to here, my moment values are the values at A, it's 1, at B, and at C. So I need to get MA, MB, and MC. Of course, I have here also my M1 and M2 as my end moments. Okay, so the new formula now is a little bit more involved compared to the old formula. Okay, now we are going to execute or perform the computation on the given problem later, and the bulk, and we will note that the bulk of the computation lies on the determination of mode. Okay, which formula now is more conservative, more advantageous? It depends. No? So there's no exact pattern to make a conclusion on the conservativeness and efficiency of the formula, but the comparison may be look into perhaps more on which is the the the, the better formula to take into account the shape of the moment diagram. Okay, because we all know that moment diagrams have different shape like uh, uniform and moments. The shape can be a rectangle like this, no? So the moment diagram, it can also be a triangular shape. So this is a rectangular. So it can be like this. And it can also be parabolic. Okay, so something like this. So take note that this is a moment gradient. It's the gradient that counts. So the gradient is actually the slope of this. Okay, so when you say slope or gradient, we are referring to the variation of the moment diagram. So this is now a linearly increasing slope, and this is a linearly, sorry, parabolically decreasing slope. Okay, something like this. So it will depend on how the moment diagram varies to account for the effect of the modification factor on your beam capacity. Okay, so dyan nagkakaiba-iba yan. So which formula fits most? So in general, it is said that the new formula is more applicable for nonlinear variation of moment with no reversal of curvature, and this formula here is not practical to use on uh, moment diagrams with a very small variation of uh, magnitude. Okay, so we will try to look into these things when we go solving a problem on this. So let's have one simple example on how to determine the moment gradient factor for a simply supported beam with a uniform load. Okay, so the load is uniform. Very easy to draw the moment diagram for a uniform load. The moment diagram is simply a parabolic moment diagram. And the lateral brace is at the ends and the quarter points. So the lateral bracing, if this is my moment diagram, is here at the ends and at the quarter points. Okay, mid, then I have it here, and also I have it here. So I have actually my 1, 2, 3, 4, 5 brace points. Okay, so the maximum moment can be solved by simply using a WL squared over 8. Okay, so this is simply your M max, or M at this point, let's call it M3, okay, is equal to a WL squared uh, over 8. Okay, so if I consider now symmetry, I can say that segment 1, 2 is simply equal to segment 4, 5. And segment 2, 3 is just the same as segment 3, 4. So what I did here is I make use of a program to capture automatically my moments MA, MB, and MC. Okay, so these are now the quarter points of your segment, not the quarter points of the problem, the beam problem. So MB, MC. So I'm referring to segment 1 to segment 2 only. Okay, the segment 2 lang ako. So I'm referring to this as my segment. Okay, segment 1, 2. Segment 4, 5. They are just the same. Okay, so how do I get the moment? So I need to make use of a formula, and the formula is simply this one above. And this is only applicable, take note, for uniform loading. Uniformly loaded, simply supported. Okay? So this is WL over 2, x minus W x squared over 2, where x is the distance, okay? X is the distance from the left support. So all I have to do is to get the values of your x in order to get your moment. Okay? So how do I get the value of x? So I simply divide segment 1 to 2 is 2.5 meters. I simply divide it. So x here is 0.75, x here is 1.25, and x here is 1 point, or sorry, yes, 1 point, this is x is point, this is not 0.75, this is 0.625, okay? So x here is, so let's remove the letter x, no? Para mas malinaw. So this is 0.625, 1.25, and 1.875. Okay, these are the values. Okay, so I divide it into 4, and I just plug it on the equation m x. Let's say m at x is equal to WL over 2. Okay, so this WL over 2 is actually my reaction R1, no? Times your x value minus W, the x value squared all over 2. Okay, so if I plug in 0.625, 1 by 1, 1.25, etc., I would get the corresponding values for your moment. So this is now my moment A, my moment B, my moment C. Of course, my moment 2 is simply computed by substituting 2.5. So this is my moment 2. This is my moment 1. And I choose the maximum. where's the maximum? So here is the maximum moment here. Okay, it's equal to m sub 2. So you are referring to this segment alone. So after doing that, I now am ready to use the 2 formula. Okay, so I just plug in my 1961 formula the value of my m1 here, which is 0, and the value of m2 here, which is m2 at 2.5. Okay, so what's your m2 at 2.5? So it is 140 140.625. Okay, so I just substitute it there and I get 1.75. Now if I use the 1993 formula, I put here my m max, this is m max, which is m sub 2. So I put in here my MA, I put here my MB, I put in here my MC, and I put here in here my sorry, this is M max, okay, M2, MA, MB, and MC. So I get 1.523. Okay, so that's how these two values were obtained, and comparing the two, which is more conservative. So here, this is more conservative and this is more economical. But you can use either of the two. If you are looking into a more economical value, you use 1.75. If you are using for a more conservative value, you can use 1.52 for that particular segment alone. So for segment 2, 3, and 3, 4, you just make use or change the range into which your moments are determined. Again, you get your segment 2, your segment 3, and then you cut it into A, B, C. Okay, so what are your x's? Your x here is 2.5, your x here is 3.125, your x here is 3.75, your x here is 4.375, and your x here is 5.0. So you just divide this into 4. So take note that this is your segment 2 to 3, which comprise the moment diagram on that segment. And of course, the value of the moments are those which are solved using the formula mx is equal to the reaction WL over 2 times x minus WL or WX squared over 2. Okay, so this is the values of that were not obtained or were not placed in the graph, but direct substitution will yield to you to values that will substitute be the substitute for this now your M1, okay, and this is now your M2, and this is your M max, this is your M max, this is your MA, this is your MB, and this is your MC. Take note that M max is the M5 or M3 that I'm referring to. Okay, so this is equal to M3 here. M at x equals 5 is simply the M3. Okay, and notice that the values again, this is the more economical, and this is the more conservative value. Okay, so that's how problems on CB is computed. And of course, the difficulty of the problem lies on the moment diagram. So I'd like you to try solving a simple beam with a point load at the midspan and brace laterally at the ends and at the quarter points. Okay, so you may neglect first the beam weight for simplicity, and also try solving a fixed end beam with a uniform loading and brace laterally at the ends and at the quarter points. Also, you neglect the beam weight. Okay, so this is now referring to a beam like this with a concentrated load P, okay, and also a fixed end beam with a uniform load W. Okay, so this is your L, this is your L. It's fixed. You neglect the beam weight first. Okay, for simplicity. Now, if you add the beam weight, this will have a uniform load, a small uniform load there, and this will have an additional uniform load here. But for simplicity, I just like you to neglect the beam weight and try this for your exercise. Okay, so that's it for this particular topic on modification factor moment gradient CB. Thank you very much for listening.